Section 15.4, Pendulums and Circular Motion. Right, so a simple pendulum is what we will most often consider. It's an approximation of a physical pendulum. It says that we have a bob of mass m suspended from an unstretchable massless string, that we only have to worry about that mass being on the very edge of that string, right? So here it's shown where the string has length L, the bob has mass m, that is where all of the mass is, so we don't have to worry about the string contributing anything. It's attached to a pivot point from above and allowed to swing back and forth, oscillating to either side of its equilibrium vertical position. Now, once it gets pulled to one side, the bob feels a restoring torque, which you could show could be calculated with the length of the string times the force of gravity times sine of the angle between those. Now, more often than not, rather than focusing on any possible angle, we look at a small angular amplitude where theta max isn't too big in terms of how far out it swings. In that case, sine of theta is approximately equal to theta. This may feel a little bit hand-wavy to you, but it actually is a well-established thing, so much so that people even make memes about it. At least engineering meme makers do. So when sine of theta equals theta, you can see theta says, okay, so basically I'm very small. And that's the short of it, right? You can try this out on your calculator. Plug in small amounts, small angles, and if you check sine of that angle versus the angle, it's basically the same thing. It works, I'd say certainly up to 5 degrees, maybe up to 10 degrees. One caveat though is that we'll have to switch back to radians for the math to work out properly. So looking at that, we can use sine of theta is equal to theta. That now becomes theta. And we can say, hey, torque, we know torque by Newton's second law, the rotational form, torque is equal to I alpha. So if we plug in I alpha, alpha is our angular acceleration, we divide our I to the other side, mg just comes from the force of gravity. And so we get this equation that the angular acceleration is equal to negative mg times the length of the string divided by the moment of inertia, or rotational inertia I, times the angular displacement theta. This tells us that the angular acceleration is proportional to the angular position, but opposite in sign. And we've seen this before, right? Remember, we saw the acceleration of our spring is equal to negative omega squared times our displacement, x. A equals negative omega squared x. So we can say, hey, this is the exact same form, right? This matches up. So since the acceleration is proportional to this position with the opposite sign, we can say that everything besides the position or acceleration of the negative sign is just the angular frequency squared. So we're going to set those two things equal to each other. So if we do that, go into the next slide, we get that the angular frequency then is the square root of mgl divided by I. Now note, we still are making the assumption that the angular amplitude is small in order for this to be true, but that gives us the angular frequency. And then if it's a simple pendulum, we know that the moment of inertia is just going to come from the mass on the end of it. We don't have to worry about the string. So the rotational inertia will just be mr squared, which the radius here is L. So we can calculate I with ml squared. So we plug that in, then we'll find that one of the L's cancel and the mass cancels out. To get to the period, we note that we'll have to flip everything and have a 2 pi factor in there. So we end up with period is equal to 2 pi the square root of L over G. This is an equation that we saw back in our pendulum lab, that the period of this simple pendulum just depends on how long the pendulum is and gravity, basically what planet you're on. Now, a physical pendulum has a more complicated mass distribution. So here's an example with what looks like a bowling pin, right? So not all the mass of the bowling pin is at the very furthest edge of it. Instead, the center of mass is somewhere offset of the edge. So we're going to have the same basic analysis for this, except rather than the full length L, we'll have the distance h from the pivot point to the center of mass. And then I, the rotational inertia, will be particular to whatever mass distribution you choose. So if it's a rod, you can plug in the rod equation. If it's a slab, you could plug in the rectangular slab equation. And you could show that the period then is equal to 2 pi times the square root of I, the rotational inertia, divided by mgh. So very similar to our last one. Indeed, if you plugged in mgh squared on top, it would look basically the same with an h instead of an L. But this just leaves it a little more general if we want to plug in something with a different rotational inertia equation. Now note, a physical pendulum will not show this simple harmonic motion if you pivot about its center of mass. About the center of mass, there's no net restoring torque because it balances out. That's why, and indeed about the center of mass, h would also come out to 0. So that's why the period would be 0. The center of oscillation of a physical pendulum is the length L0 of the simple pendulum with the same period. So we can say that physical pendulum is like a simple pendulum with a modified length. Physical pendulum can be used to determine the free fall acceleration g. This is what we did in lab with the simulation. So assuming the pendulum is a uniform rod of length L, then we can say, hey, what's the rotational inertia? Well, the rotational inertia about the center of mass of a rod is 1/12 ml squared. But we here are not pivoting about the center of mass because we wouldn't have simple harmonic motion if we did. So we're going to use the parallel axis theorem to shift our rotation axis from the center to h distance away. That's the only time we use the parallel axis theorem. And so we can shift it to the end of the rod, right, which is half of a length away. So that's why for h, we plugged in 1/2 of L. That gets squared, so it becomes 1/4 L squared. And if we add that to 1/12 ml squared, we get 1/3 ml squared. So if we go back and plug this in for the I in the previous equation, we'll notice that one of the L's will cancel, the masses will cancel, and we can rearrange to solve for g. That for a thin rod, the acceleration due to gravity can be calculated with 8 pi squared times the length of the rod divided by 3 divided by the period squared. This is very similar to the equation that you indeed used to calculate g. We just used more of a simple pendulum and not a physical pendulum like this rod. All right, let's look at a checkpoint here. 3 physical pendulums of masses m0, 2m0, and 3m0 have the same shape and size and are suspended at the same point. Rank the masses according to the periods of the pendulums greatest first. All right, so please consult your equations, your notes, come up with an answer here. And while you're thinking about it, go ahead and push pause. All right, did you push pause? Okay, well, let's take a look. I hope you already have your answer. D, all the same. Mass does not affect the period of a pendulum. Now, some of you might be thinking, but wait, I saw mass in the physical pendulum equation. It canceled out in the simple pendulum, but not in the physical pendulum period. And let's take a look at that. You're right. There is mass in this period equation. It's right there. So if we have more mass in the denominator, shouldn't we have a smaller period? Well, there is a catch in this, and that's that we have the rotational inertia in the numerator. And I is always proportional to mass. In every iteration of it, it's usually mass times some distance squared, like mr squared, ml squared. And then there might be a number like a 1/2, 1/3, 1/12 in front of it. But there's always direct proportionality between the rotational inertia and the mass. And so the masses are going to cancel out. And we find that the period doesn't depend on mass. It just depends on how that mass is distributed and how long it is. So that's pretty wild here. And we can keep going. So the other thing to consider is this idea of circular motion. There's a really nice video by Crash Course in Physics that takes a look at how circular motion is related to simple harmonic motion. I encourage you to take the time to watch it. The presenter is very talented at explaining it very succinctly, much more so than I am. So please, that's going to be your best use of time. But the short of it is that simple harmonic motion is circular motion viewed from the edge. So it's the projection of uniform circular motion onto a diameter of the circle in which the circular motion occurs. And there's much better visuals in the video, but it's basically here we have something moving in a circle, and the radius of the circle is set by the amplitude, xm, and then the projection onto the x-axis tells us the displacement at a given instant in time. So if it's all the way, if it starts out here at an angle of 0 degrees, it's at a maximum displacement, but then as it rotates towards y, the displacement becomes smaller and smaller until it's 0. And that angular position is set by the phase of the cosine. So omega times the angular frequency times the time plus the phase angle. You can also look at the velocity and the projection of the velocity vector onto the x-axis to note how fast it's going. You notice then at angle of 0, there's no projection onto the x-axis, it's going purely vertically. But by the time it makes it around to 90 degrees or pi over 2, it's going purely in that direction. You're at your max velocity when you're at a displacement of 0. So it indeed all works out. You can even look at the acceleration and set that the amplitude of the acceleration, which is the max value you could have, and the projection tells you the value at any given instant, which is at a max when the displacement is at a maximum value. So here's a nice visual of that, where as you rotate around the circle, the projection onto the x-axis traces out the sine or the cosine wave, the sinusoidal function. Oh, I could just sit here and watch this all day. It's pretty amazing, right? I hope you can see. So we're doing this with position, but it also works with velocity and acceleration. So this projection is simple harmonic motion. Pretty wild, pretty nifty. That is where we will wrap this section up.